Hello, everyone. Welcome to our webinar today at Statistical Solutions. My name is Justin D'Souza. I'm a quantitative specialist here at the company. During today's webinar, we are going to cover the verification of statistical assumptions. So really covering the key assumptions that I see used the most often that sometimes give some trouble to students. I'll be using SPSS to kind of give some examples. We're going to send everyone a copy of the webinar as well as a copy of the PowerPoint. My colleague Sierra has provided some hyperlinks in the chat box for dissertation resources. You can view our previous webinar archive. If you have any questions about previous topics that we've done, we cover every part of the dissertation journey and we do a webinar on them. You know, the introduction, the review, theoretical foundations, developing research questions, pinpointing a specific analysis to use. And then there's also a link to schedule a consultation if you have any questions about the services that we provide. Go ahead and dive in. So the first thing I'll cover is a brief overview of the services that we cover at Solutions. Then we'll dive into today's topic about statistical assumptions, primarily for inferential analyses. Then we'll give a demonstration in SPSS as to how to conduct these analyses. And we'll conclude with a summary and a question and answer session. On this slide, you can see all the different components that we assist with at Statistical Solutions. We offer packages for assistance, and we also provide hourly consulting. We have literature review specialists, as well as methodologists, quantitative and qualitative. So no matter where you are in the process, if you hit a roadblock, we can provide assistance to help you get over that hump and get you through to the finish line. Just give us a call if you have any questions at 727-442-4290. So the primary assumption that I would say most students get kind of tripped up on is normality. And whenever you're running inferential analyses, specifically parametric analyses, you know, these are things like correlations, Pearson correlations, t-tests, ANOVAs, regression models, you have to verify normality on your dependent variables. You have to make sure that your data follows a bell-shaped curve or a bell-shaped distribution. And depending on the reference you read, there are numerous ways to check for this assumption. And check for it objectively with a Shapiro-Wilk test or a Kolmogorov-Smirnov test, or you can use visual interpretations like grams, bar charts, or normal QQ plots or PP plots. The tricky thing is that sometimes you might check it one way, and if you check it a second way, the findings might contradict one another. You might see normality supported objectively, but visually it might not look so good. The main thing you have to keep in mind is select a method and justify it. Oftentimes you only need to select one method and just proceed from there. Sometimes the findings will contradict one another, so you don't want to use multiple methods. Just select one and roll with it. So for the objective test, we have Shapiro-Wilk tests and Kolmogorov-Smirnov tests. And I think what's confusing about this for many students is that you want to see non-significance. You want to see a non-significant result on this test, meaning that, you know, when you look at p-values, you usually hope for a p-value below 0.05. But on these tests, significance means that your data is significantly different than a bell-shaped curve or normal distribution, which is not ideal. And the visual interpretations are looking at histograms and QQ plots and PP plots. And these are kind of subjective, you know, depending on who looks at a plot, they might say, hey, this looks like a normal distribution, and other people might not. So I tend to go with the objective test. It's kind of clear cut. Is the assumption met or is it not met? And if your assumption of normality is violated, it's not supported, then you might want to consider shifting to a non-parametric approach or consider transforming your data. So most analyses like Pearson correlations, they have a non-parametric alternative, a Spearman correlation, or Kendall's tau correlation. Same with like tests of differences. If you propose to do an independent t-test, you need to check for normality on your dependent variable. And if the assumption is violated, you can shift to a Mann-Whitney test. Or if you're doing ANOVAs, you can shift to a Kruskal-Wallis test. So that's usually the solution, is shift to a non-parametric approach. You can consider transformations, which is, transforming your data to a different distribution, like a logarithmic distribution or a parabola, a parabolic distribution. I tend to avoid those because it shifts the interpretation of your data. I don't love interpreting data in terms of logs or I-squares or different transformations. I like to keep the original format of the data. You can also try to remove outliers. If you do run a Shapiro-Wilk or Kolmogorov-Smirnov test and the test is violated, you can see if you have outliers in your data, and I'll show you how to do that in just a moment. But sometimes outliers can skew your data, which makes it not appear like a bell-shaped curve. Let's take a look at an example first to verify normality. I do have a sample spreadsheet here. If you've joined us before, I've been using the same spreadsheet for consistency. So, all the clients can understand what's going on here. But if you haven't joined us before, the spreadsheet contains different car models. We have Mazdas, we have Chryslers, Honda Civics, Corollas, and you can see the variables of interest. We have miles per gallon, horsepower, the weight of the car, quarter mile time, things like that. So to test for normality in SPSS, there are many menus you can select to do this, but the most efficient way I do it is by going from Analyze to Descriptive Statistics, and then Explore. And then just put in your variables of interest. Say we're just looking at miles per gallon and horsepower. You put those into the right box, and then you need to go to Plots, and we will check mark this box right here, Normality Plots with Tests. This is going to generate the Shapiro-Wilk and Kolmogorov-Smirnov tests. And then you can also check mark a histogram, so you can see a visual representation of the data. We'll click Continue and OK. And let's see how this looks. So as we scroll down, here we have the objective tests, Kolmogorov-Smirnov and Shapiro-Wilk. So as I examine the p-values, which are under the significance columns right here, remember I said that p-values below 0.05 are actually not ideal. That means that the data does not follow a normal distribution. So that applies to horsepower. We go across the row for horsepower. Horsepower has a p-value below 0.05 on the Kolmogorov-Smirnov test, and it also has a p-value below 0.05 on the Shapiro-Wilk test. But both of these tests indicate that horsepower does not meet a normal distribution, at which point I would probably shift whatever approach I'm using with horsepower and use a non-parametric test instead of a parametric test. Miles per gallon, we can see that the p-values are greater than 0.05, meaning that the assumption of normality is supported for mileage. And we can look at more visual interpretations. Again, I don't really like these, especially if you have a smaller sample size. I will always cater to running a Kolmogorov-Smirnov or Shapiro-Wilk. But you can see the distributions of the data. It's more difficult to support normality with a smaller sample size and a visual representation. So here is also presented the QQ plot. And ideally, you want your data, which are these little blue circles, you want it to follow this normality trend line, which it does quite closely. And then we have box plots. We'll talk about that when we get to outliers. Histogram right here for horsepower, we can see it's heavily skewed to the right. And then the normal QQ plot does show some deviations. It's deviating from the normality trend line. So normality, I would say, is not supported with horsepower. multiple ways. First off being the Shapiro-Wilk and Kolmogorov-Smirnov tests. Then the histogram does not resemble a bell-shaped curve. And the normal QQ plot, it's not following this diagonal trend line perfectly. So that's normality. The next assumption is kind of a continuation on this. Say you want to look at outliers. So to remove outliers is something to consider early on. Sometimes you don't want to, if you're looking at test scores or you're looking at, test scores is the best example because sometimes you don't want to remove cases that have extremely high or low scores because keeping those cases in will depict how people are actually scoring, and taking them out is taking away the truth of how people are scoring on scores or scoring on tests. But sometimes you do want to remove outliers because it will skew your data in one direction if you have an extremely high or extremely low score. So there are a couple ways to do this as well. I provided a citation here to Bachnick and Fidel. They indicate that outliers correspond to z-scores that exceed positive or negative 3.29 standard deviations from the mean or the average. And then you can also use box plots to visually identify outliers. And then consider removing these cases and see if that improves normality. So to check this both ways, the first way is using z-scores, and that's just a standardized value around your mean. To do that, you will go to Analyze, Descriptive Statistics, and Descriptives. Then we'll put in the variables of interest for the sake of consistency. Again, let's just use miles per gallon and horsepower. And then before you click OK, check mark this box right here, save standardized values as variables, and then click OK. What this is going to do once I click OK is it's going to create two new variables of interest representing miles per gallon and horsepower, but these two new variables will be z-scores now. Okay, so now you can see at the beginning here, we have z miles per gallon, z horsepower. And using the citation, they say that if a value exceeds positive 3.29 or if it is below negative 3.29, that is most likely an outlier. So let me move these two variables over here just so we have them side by side. And what you do is you just right click on the z-score and you sort in ascending order and then you sort in descending order. So let's do ascending first. And we can see the lowest z-score is negative 1.61, and that is not below negative 3.29. So this 10.4 is not an outlier. Then we'll do miles per gallon in descending order. And we can see that the highest was 33.9, and the z-score to accompany this is 2.29. That is not greater than 3.29, so we are in good shape. Then we do the same thing with horsepower, sort in ascending order. So this 52 horsepower car is not a low outlier. And then we sort in descending order. And we have a case here, this 3.53 is larger than 3.29. So that means that this car that has 460 horsepower, it is a Maserati, that is most likely an outlier. So we should consider taking it out. It's kind of a test and retest situation. Like I said, sometimes you want to keep outliers in so you can maintain a realistic depiction of the data. But sometimes to fix normality, this is a solution. And you could consider taking this case out. Okay, so that is the z-score method. You can also look at box plots, which we already generated. It should be in the output, but just to do it again, we'll go to Descriptive Statistics and Explore, and then under plots, everything should be good in here. I don't think you have to check mark anything specifically, but you'll see as we scroll down to the box plots, here is the box plot for mileage. And Because we see no points going beyond the whiskers, that means we have no outliers on mileage. And we'll look at horsepower, and you can see that we have 2 points of interest here. This number 1 star, that is the Maserati. Outliers will have stars or asterisk like this. Points that are outside of the norm, not necessarily outliers, will have a circle. So, you know, this case 2 is this one right here, 350, which was a Ford Pantera. I would not remove that case, but I would consider removing the Maserati case. That's number 1 right here. It had 450 horsepower. Okay, so stars are outliers, circles are kind of influential points. You don't necessarily need to remove those. Okay, the next assumption is homogeneity of variance. And this is run when you're looking at t-tests or you're looking at ANOVAs. And it's the assumption that is making sure that the spread of your data is approximately equal between your groups. So say we're looking at job satisfaction between males and females, you would run a t-test, and homogeneity of variance is making sure that the spread of job satisfaction is approximately equal between males and females. Okay, so let's do a hypothetical t-test on this. Go to compare means, independent sample t-test. And in this example, let's do, again, we'll do mileage and horsepower. And let's see if there's a difference by transmission type. You know, if a car is automatic or manual. You need to use this one. You need to have a numeric grouping variable. So I just took manual and automatic and converted it to 1 and 2 for the coding. Okay. So Levine's test is right here. This is the test for homogeneity of variance. And you'll see that for each t-test, there are 2 rows of data. If the assumption is met, then you use this equal variances assumed row. If the assumption is not met, then you use equal variances not assumed. Similar to the Shapiro-Wilk and Kolmogorov-Smirnov tests, significance is actually not a good thing on these tests. You want to have non-significance. So what we look at first is Levine's test. What is the result of this? For mileage, we have a 0.021 p-value, which means the assumption was violated. We do not have equal variances between automatic and manual cars. We can actually see that up here, that there's quite a difference between the 2. So then, because this assumption was violated, we're going to use this row right here for the t-test. You would use the negative 3.77 and this p-value, 0.001. For horsepower, we can see that the p-value was greater than 0.05, meaning that the assumption of homogeneity of variance was supported for horsepower. Therefore, we would use the first row for the t-test. Equal variance is assumed. So 0.54 and the p-value 0.59. So I discussed that here. If the assumption is not supported on a t-test, use the equal variance is not assumed statistic. And if you're doing correlations or you're doing regression models, linearity is usually one of the assumptions. And to test this, it's pretty straightforward. You just run a scatter plot. You run a scatter plot between your independent or your predictor variables and your dependent variables. And if the data follows a linear trend, like you can clearly see a positive or negative inverse trend, then you have support for linearity. And so for example, here, say we to do a scatter plot, you go to graphs and then chart builder. And what we'll do, let's just reset this. This is what it looks like from scratch. We'll go to scatter, which is around the middle of the choose from gallery. And then you'll drag a scatter plot up here. And for example, if we look at miles per gallon and weight of the car, and then click OK, we can see clearly that the more mileage you have, the less weight of the car. Weight is measured in metric tons on the side here. And you can also add a regression line to this. If you double click, now you can edit the plot. And if you go to elements and put fit line at total, that is going to give you the average regression line that supports this data. So in this case, I would say linearity is supported. And the next assumption is if you're running a multiple linear regression, the assumption is called absence of multicollinearity. And this is making sure that your predictor variables, when you do a multiple regression, you have multiple predictors. And this assumption is making sure that your predictors are not highly associated with one another. So we use something called variance inflation factors to test this assumption. And if the VIFs for short, if these are below 10, then the assumption is supported. So for example, we'll go to analyze regression. I'll do a linear regression. And say we're trying to predict mileage. And we'll put in displacement, weight, horsepower over here as predictors. The key thing, I'll show you all the assumptions here for linear regression. So you'll go to plots first, and to look at normality, you have to do a normal PP scatter plot. You're going to check mark this box at the bottom. Then to do homoscedasticity, which is similar to homogeneity of variance, you put in your Z predictor here and the Z residual right here, and then click continue. Then we'll go to the statistics box right here, and we will check mark collinearity diagnostics. This is going to give you the variance inflation factors to check for absence of multicollinearity. We'll click continue, and let's go ahead and run it. Click OK. Okay, so the first couple assumptions are at the bottom. Here we have a normal PP scatter plot, and it looks acceptable. It doesn't look great, I'll say, but that's because we have a relatively low sample size. So, when you do a data collection and you're running regression models, you need to aim for more than 30 cases. What we have here, 32 cases. The larger your sample size, the better this tends to look. Then we have our second residual scatter plot here to look at homoscedasticity. Homogeneity of variance is it's a synonym for that. And in this scatter plot, you just want to see the absence of a pattern. You don't want to see a straight line. You don't want to see an exponential curve or a box. You just want to see a random scatter, which we do have here. So homoscedasticity is supported. And then absence of multicollinearity is presented in this coefficients box. If you look at the VIF column right here, as I mentioned in the PowerPoint, if the VIFs are below 10, then that means that the predictors, displacement, weight, and horsepower, are independent of one another. They are not influencing one another. So that is supported. If the VIFs were larger than 10, then I would consider removing certain predictors, see if that improves the model. Okay, so that covers the primary assumptions that I see used. You can also take a look if you type in, say you're doing a t-test, and you put statistics layered here. Statistics layered is a great resource that they explain how to do things in SPSS. So if you put any analysis, regressions, t-tests, ANOVAs, and then just type statistics layered after it, they will give a breakdown of what assumptions you should check. Okay, I see GCU, a lot of universities do reference this now. So for a t-test, here are the examples. A lot of them are just foundational. Your dependent variable needs to be measured continuously. That's kind of a given. The independent variable needs to have two discrete groups. You need to have independence of observations, meaning that one participant cannot be in two groups. Like if you have employed and unemployed, you can't be in both groups at once. Not have significant outliers, so we discussed that. The data needs to be approximately normal in distribution, and we need homogeneity of variance. So we kind of covered all of these for a t-test. Okay, great resource. So we'll do a Q&A session if you have any questions. I see some people joined just recently. We will be sending a copy of the recording and the webinar to everyone. But if you have any questions, you can type those into the chat box. You have questions about assumptions. And Sierra has provided some hyperlinks in the chat box as well. Any questions about analyses to run, suggestions on assumptions, how to run certain things in SPSS? If you have any questions, you can type those into the Q&A or the chat box. Here's our company website. You can see what webinars we have done in the past at the archive library, and you can see what is upcoming. Okay, so it looks like we have a couple more for August, and then September we'll have about 8 new webinars in September. Okay, so surviving your dissertation and mastering the introduction chapter are coming up next. Okay, no questions? Questions about assumption testing? We have a question from Nadia about intellected statistics. Intellected statistics, if you haven't joined us before, that is our company software that we've developed to test and run data. So let's take a look at that. Let me just log in here. I believe we do a free trial for a week. So within Intellectus, you can really pinpoint what analysis you need to run. We have a decision tree here that guides you in the right direction for a specific analysis. I want to explore for differences over time. That will start the decision tree. I have one dependent variable. Are the participants divided into groups? Yes, no covariates. You should probably run a mixed model ANOVA. So this will guide you in the right direction. And then we also have data analysis plans. So kind of going off that, a mixed model ANOVA. It will give you a sample research question and hypotheses and give you a definition of a mixed model ANOVA or whatever test you're running, and discuss the assumptions that should be verified. Then we go into power analyses, in which you can figure out what is the minimum sample size you need to target. So say we have 2 categories and we have 3 measurements of time. You should target around 28 people. This is based on a power analysis conducted in G-Power, the software here. So Nadia asked a question about hierarchical regression. We do have that in here. So let's see, maybe it's not actually, it's under here, data analysis plans. and hierarchical linear regression. So it's in our data analysis plans, but you can also run the analysis once you have your data right here. Be consistent, use the same. So here's the car model data set. You can see all the data management functions that we have: removing outliers, transforming data, imputation, reverse coding. And then you can run the analyses in here. So if we go to regressions and a hierarchical linear regression, you put in a dependent variable first, such as mileage. And then you need to put in variables sequentially. So you put in, say, horsepower in the first step. And then in the second step, say we put the weight of the car. And so this is how a hierarchical regression is run, and this is how Intellectus provides a write-up for you. We just ran the model, and it gives you a full APA interpretation. It's pretty cool, really efficient. So it's going to test for normality on both step 1 and step 2. Test for homoscedasticity, absence of multicollinearity, all the things we discussed in SPSS. And then it provides an interpretation. Is there a significant model? And what is significant? You see that as horsepower increases, miles per gallon decreases. And this is all APA format. Does that make sense? Do you have a specific question about hierarchical regression? I just see that some additional people joined recently. We're going to send everyone a copy of the recording and the PowerPoint. Okay, and I believe there's a free 1 week to use Intellectus. But if you have any questions about the software or the services we provide, you can give us a call at 727-442-4290. Or you can email us here. Okay, Nadia, did you have any other questions about Intellectus? Sounds good. Thanks for joining. All right, do we have any other questions? All righty. Well, have a great evening, everyone. We'll send everyone a copy of the recording, and we'll be doing a couple more webinars this month. Good evening and take care.